All right, here we are for section 4.2. We're going to start throwing some numbers into our sine and cosine function and we're going to see how that changes the graph. This section is going to all be about stretching or shrinking, or more generally scaling the graph horizontally or vertically. All right. And so the first thing we're going to do, now we'll just look at the filled in version, we're going to take these functions and multiply them by a number. So imagine you plug in your angle, you do the sine of that angle, you get some number, and then you just multiply by this capital A. So what does that do? Well, it changes the amplitude. All right, so that now when you multiply by that number, we had an amplitude of 1 before. All right, remember amplitude is the distance from the center, horizontal center of the graph to the up to the top, down to the bottom, the peaks and the valleys. Now, whatever you multiply by, the new amplitude is the absolute value of that number. And we say absolute value because amplitude is always a positive number, even when A is negative. We'll talk about what happens to the graph when A is a negative number. All right? But this, stretches the graph. So let me show you. So I have this little demo on Desmos. And you can see this function up here. There's a capital A and a capital B and a lowercase k and a lowercase h all involved there. We'll get to all of those. Right now we're just talking about what this capital A does. And basically, when we have the regular sine and cosine function, it's 1, but we don't write it. All right, but when we change it, well, what happens? So here's our basic sine graph. All right, does its nice one cycle starting at 0. Hey, there we go, that's better. Starting at 0, does its little cycle, comes back to the beginning here at 2 pi, and then does another wave and keeps going. So when you change A, it just changes the size of the output. So it ends up stretching it. If A is bigger than 1, it ends up doing this thing. Makes the graph taller, so you can see the amplitude is changing as we change A. If you make A less than 1, well, it will start shrinking the graph, making those peaks and valleys occur at higher and lower, or at points that are closer to the center as well. Right, so we're just changing the amplitude. It still goes through 0 in the same spot. It still finishes its wave at 2 pi. It's just changing the vertical distance, or where the peaks and the valleys occur. All right, so in terms of sketching a graph, what we're going to do with these graphs is to make a sketch of one complete cycle of that thing. And the way we're going to do that is basically to figure out where 5 key points are. All right, and that would be, as listed here, the beginning of one cycle, the end, and then halfway, a quarter, and 3/4 of the way through. And we use those because those correspond to the peaks and the valleys and the spots where it crosses the horizontal center line of the graph. So if this is our wave, we're talking about this point, this one, this one, this one. And if we know where those are, you can then just put that sine wave shape through those key spots. All right, so the first example is pretty straightforward, and I think we'll just look at it. So we have the function y equals 7 times sine x. So all that's changing is the amplitude. The amplitude, like you can see beneath here, is now 7. The period is still 2 pi. So our graph is going to start at 0. It's going to end at 2 pi. So I'm going to mark off 5 x locations. We have beginning, we have quarter of the way, halfway, 3/4 of the way, and the end of our one cycle. And we just have to mark off, we're going to label these points in between. So 0, 2 pi, beginning and end. These are the same as the original sine function. Pi in the middle, pi over 2, 90 degrees. A quarter of the way, and 270 or 3 pi over 2 here. And then what we know about the sine function, so we have to keep these in mind. Here's the basic sine wave shape. Here's the basic cosine wave shape. This is a sine function. And the sine function starts, and now we have, I should talk about this too, on On the vertical axis, all we mark off is where the peaks occur, where the valleys occur. And instead of happening at 1 and -1 like they do for the regular sine function, now we're at 7 and -7. So in fact, this almost looks exactly the same. We just have different numbers marked off for the peaks and the valleys. So then the sine function starts in the middle. So we have top, we have middle of our wave, and we have bottom. Sine function starts in the middle and goes up. So here it is, starting in the middle, which means at the next key point, it's going to hit a peak. From there, it can't do anything but go down. So the next key spot would be a middle of the graph. Then it keeps going down to hit the bottom, and then it just has to turn around, and the next key point would be in the middle again. So we would mark off 1, 2, 3, 4, 5 key points, and then just draw the wave on through there like so. All right, so changing the amplitude is not a real fancy change. In fact, this graph, if you go back, looks exactly like the sine graph that we had before, and the only thing that's different is that instead of 1 and -1, we have 7 and -7. Okay, we'll see more amplitude changes, but we'll keep looking at examples here too. So the other change, I'm going to set a back to its standard value of 1, is b. So what if we, and we're going to ignore -h for now, we are going to be looking at graphs that look like this. So what if we multiply the input x by a number? So you would multiply the input by b before doing the sine or the cosine function. Well, the impact that has is that when you put a different number in there, and for y equals sine x, basically b is 1, but we don't write it. If you do put something other than 1 in there, it changes the period. So the original period is 2 pi. The new period follows this formula, which is a little different. All right, so you take your standard period of 2 pi, and you divide by whatever that number is to get the new period. All right, so this is going to change the x-axis for us, right? The letter A has an impact on the y-axis. The capital B, if you multiply the input, has an impact on the x-axis instead. And so it's going to change these x values. And one key property that we are going to use in figuring out what these are is the fact that, well, look at it this way. We're going to mark off the first number and the last number. So then this number here is exactly halfway in between the beginning and the end of our cycle. And the way you find a number that's exactly halfway between the two is basically to take the average of the two it's in between. And you take an average of two numbers just by adding up and dividing by 2. So we will use this fact a lot, especially when things get messy for us on the x-axis. If we start at some x-coordinate A and end at another one, the one that's exactly halfway in between the two comes from adding these two together, dividing by 2. All right, let's get on to an example here, and we will actually do this one on the blank notes. Okay. There we go. Y equals cosine of 3x. Now, first off, there's no number written in front of the cosine, so our amplitude is just 1, which means on the vertical axis, we'll hit peaks at 1, and we'll hit valleys at -1. All right. And then along the way, we're going to have spots kind of here. So we'll have, so there's our 5 key spots. The beginning spot right here, a quarter, a half, 3/4, and the end of the whole entire cycle. Now the period, try that again. The period, we've got a 3 in here. The new period is going to be 2 pi divided by whatever that number is. So 2 pi over 3, and you can't even simplify that. So our basic graph here, still starting at 0, but now ending at 2 pi over 3, like so. Question is, what are these other 3 key points? And that's what we need to figure out. All right, so what we're going to do to find this guy is we're going to well, it's halfway in between the beginning and the end. So we would do 1/2 of adding those two guys together, like so. And if you do that, you can cancel the 2, and you get pi over 3. There it is. Now, when one of the x values has a pi involved, basically they all will, except maybe a 0. And one way you can end up thinking about these numbers is that there's going to be a pi in every single numerator, and it's really just a matter of what's the other fraction. Like, you could think of this as 1/3 times pi, and this guy is 2/3 times pi. So there's always a pi around, and it's really just a matter of what fraction of pi is this. So this guy, the one who's a quarter of the way through, is halfway in between 0 and pi over 3. So 1/2, we take our 0, we add the other end of this portion, and if we simplify that, we would just have to multiply the fractions, and we get pi over 6. So that's who goes right here. And so the last issue is who goes here. Well, he's halfway in between pi over 3 to pi over 3. All right, so we're going to do 1/2. We're going to add pi over 3 to 2 pi over 3. All right, which again is, if you sort of ignore the pi's, we're adding 1/3 of pi to 2/3 of pi. And 1/3 plus 2/3 is a whole. Well, yeah, this is, if we add them together, they already have a common denominator. A single pi plus 2 pi's is 3 pi's on top and 3 on the bottom. The 3's will cancel, and we just get 1/2 of a pi. So that's what goes here. All right. Now, sometimes figuring out these x values is the majority of the work, and can be a pain in the butt when there's fractions and there's a pi involved, which just feels weird and stuff like that. All right, but once you've got that done, the rest is simpler. Now, this is a cosine function. So what happens? Well, cosine, if you remember, that's the cosine shape. It starts at the top. So that's our first key point. From the top, the only place you can go is down. So at the next key point, we would hit the middle. There we go. And then it would keep going down, bottom out in the middle. Then it would turn around, and it would get up to here, and then it would peak right there. And once you got those 5 key points plotted, you can just, this is much nicer looking when you do it with an actual pencil. Wow, that's terrible. You get that sort of shape. So here's, yeah, the nicer looking one on the filled in notes. All right, so again, identify, or figure out your x values. There they are. Identify 1, 2, 3, 4, 5 key points, and then just draw the shape between them. That was terrible, but you get the idea. All right, another example, which I'm kind of just scrolling to more than anything else, but the numbers turn out a little bit nicer here. So let's just go through it. Number 1, there's an 8 right there. So the amplitude is 8, which means peaks at 8, valleys at -8. The period, so this 2, well, that 2 shows up right here. 2 pi over 2, the 2's cancel, so the period is just pi. So that's what goes here. Again, we're starting at 0, we'll end at pi. So then what goes the rest of the way? Well, if you think of it, this is 0, this is 1 whole pi. So this would be exactly 1/2 of a pi, so pi over 2. This would be 1/4 of a pi. This would be 3/4 of a pi, and that's exactly the fractions we wrote down. Now, you could also find these things by doing things like, well, once you've got this guy and the last one, this one would come from 1/2. We would have to add pi over 2 to pi. So that would be pi over 2, and we would need a common denominator, so we'd have to write that as 2 pi over 2. So with the common denominator, 1 pi plus 2 pi is a total of 3 pi's on top, 2 on the bottom. And if you multiply the fractions, sure enough, 3 pi over 4, and there it is. But sometimes the numbers are nice enough that you can just like figure out what these guys are. Remember, this is a quarter, a half, 3/4, and the whole way through the cycle. All right, now once you've got those guys labeled, it's just a matter of where are those 5 key points so we can draw the graph. Now this is a sine function. Sine functions start in the middle of the wave. So there's the first spot, and then the sine function goes up. So at the next key point, we'd hit the top, then we got to turn around, so middle and then bottom at the next two, back there, and then you can draw your wave through them. All right, one more example here, which we'll just kind of go through like this. First off, there's a typo. The parenthesis should be on the other side of the x, not after the pi over 4. All right, amplitude. We have negative 13 in front, so the amplitude is the absolute value of that, so positive 13. So peaks at positive 13 and valleys at negative 13. Now, pi over 4 sounds like not so much fun to deal with in there, but nice things actually happen. So the x is being multiplied by pi over 4. So the period will be 2 pi, the original period, divided by whatever that number is. That comes from here. And what's nice about that is that, well, dividing by a fraction, same as multiplying by the reciprocal. And when you multiply the two together, the pi's actually cancel, and all you get is 8, which is great because number one, it's a whole number, and number two, there's no pi in the period. That can happen. In fact, when you get a nice pi for this number inside the function, your period will usually work out to not have pi in it. So our wave starts at 0, like it always has been. It's going to end at 8. And so, well, and then you're just going to mark off a quarter and a half and 3/4 of the way through, and those numbers are really easy to figure out in this case, just 2, 4, 6, and then 8. All right, so then where are the 5 key points? Well, this is a cosine, and what we said earlier is that this is the basic cosine shape. But we have a negative number in front. And what that negative number does is that, well, it changes the amplitude, but it also flips the whole entire graph upside down over the x-axis. So, since this is a negative cosine, instead of starting at the top, our negative cosine starts down at the bottom. Right? And then it's basically, yeah, this shape, but flipped upside down through that line. So it looks like this. So from the bottom, you can only go, and you would hit the middle next, and then the top. And then you got to turn around, so you'd hit the middle at the next key point, and hit the bottom at the end, and you can draw your nice little wave shape through there. Okay. So the rest of these are group examples, group exercises. There's 4 of them. I would suggest you try them, all right? Then you can come back and look at the actual solutions. I'm going to stop this video, but I'm going to do another video where I actually go through and we'll talk through all 4 of those examples so you can see them come together. But I'm going to leave this video as it is and just upload this. So go ahead, try those group exercises. Compare them to the answers. Go watch the other video for 4.2 to get more info on those and help you figure them out. So, okay, so that's going to be the end of the 4.2 lecture notes. There will be a separate video for group exercises.